Welcome to a screencast on an introduction to pH and pOH. The objectives of this screencast are to express hydronium and hydroxide ion concentrations on the pH and pOH scales, to define pH and pOH and perform calculations relating pH and pOH, and to write the ion product constant for water or the auto-ionization of water, and use this to calculate hydronium and hydroxide ion concentrations. Now, one way we can quantify acids and bases is in terms of the concentration of the hydronium ion in a solution, or shorthand H+ ion in solution, and this can vary over a really big range. We define something often called the power of hydrogen as the following: pH equals negative log base 10 of the hydronium ion concentration. You've probably heard of pH before, and this is its mathematical relationship, and sometimes we write it in shorthand: pH equals negative log of H+ concentration. Now, the pH scale, we often say it ranges from 1 to 14, but in fact you can have pH lower than 1. You can even have negative pH. You can have pH higher than 14. But most substances probably fall within that general range. And pH is a function of hydronium ion concentration in a solution. And it's a negative logarithmic, in fact, relationship. And so a pH of 1 corresponds to a 10 to the minus 1 or 0.1 molar hydronium ion concentration in solution. A pH of 2 corresponds to 10 to the minus 2 molar hydronium ion concentration, or 0.01. pH of 3 is 10 to the minus 3rd molar, pH of 4, 10 to the minus 4th, and keep on going through, at least on this chart, 10 to the minus 14th corresponds, for that molarity, that's a pH of 14. So notice the huge range of concentrations, and of course we can have higher concentrations out this way and lower concentrations of hydronium this way, but many orders of magnitude range of hydronium ion concentration. On the pH scale, we've made it into just a it looks linear, but it's really not scale. pH of 7 is neutral, and pH below 7 is acidic. The lower it is, the more acidic it is. And a pH above 7 is a basic solution, and the higher above 7 it is, the more basic the solution. Note that the larger the H3O+ concentration, the lower the pH. So as H3O+ concentration gets bigger, pH is lower. And of course, vice versa, as H3O+ concentration is smaller, pH is higher. Now, let's apply this to a calculation. The question is, what's the pH of 0.10 molar nitric acid? Well, the pH of anything is going to be calculated by taking the negative log base 10 of the hydronium ion concentration. So note, we're not taking directly the negative log base 10 of the stated concentration. We need the hydronium ion concentration. Now, in this case, since nitric acid is a strong acid, and since strong acids fully dissociate, then 0.1 molar HNO3 produces 0.1 molar H3O+, and now we can actually use this equation. So in general, we're going to have to figure out the H3O+ concentration. In the case of a strong acid, it happens to be exactly the molarity of the solution, but generally speaking, that's not something we can assume. Well, in this case, it is the case. So negative log base 10 of 0.1 molar is negative log base 10 of 1 times 10 to the minus first, kind of showing explicitly the exponent here. And this happens to be an easy number. Negative log base 10 of 1 times 10 to the minus first is negative 1, which is positive 1. And so with the right significant digits, the pH of this solution is 1.00 molar. If we had a more concentrated nitric acid solution, we can get a pH of 0 or even a pH of negative values as the solution for a more highly concentrated nitric acid solution. Now, what about the other way around? What if we know the pH, can we figure out the H3O plus concentration? Well, here's an example. Blood has a pH of about 7.40. What's the H3O plus concentration in blood? And the relationship we have is this pH equals negative log base 10 of H3O plus. Now, if we have an equation and we use both sides of the equation as exponents of the same value, it's still an equation. In other words, 10 to the minus pH is equal to 10 to the log base 10 of H3O plus, because the exponents are equal, therefore 10 to each of these equal exponents is also equal. And the reason we did this is that 10 to some power and log base 10 are inverse functions of each other. So they actually essentially cancel each other out, and this reduces then to 10 to the minus pH equals H3O plus, and that is a generally true relationship. H3O plus equals 10 to the minus pH is essentially inverting the pH definition equation and solving for H3O plus is in terms of pH rather than the other way around. We'll apply this generally true relationship to the specific of this problem, which is a pH is 7.4, so 10 to the minus 7.4 equals the H3O plus concentration, and that works out to be 4.0 times 10 to the minus 8th molar. Notice that this equation applies when we use H3O plus concentrations in units of molarity, and the number we solve for, 10 to the minus pH, is going, whatever number we get, that will be the molarity. And when we know a molarity and we take when we want the pH, we have to have our H3O plus concentration in molarity units before we take negative log base 10 if we want to get the correct answers. Okay, now let's go a little bit further with this. We've looked at H3O plus and its relationship to pH, and we're mostly going to deal with aqueous solutions, so let's continue looking at aqueous solutions. And here's a molecular level representation of pure water, a bunch of H2O molecules in there. Now, if you look closely, you'll notice there are a couple of not H2O molecules. Here we have a hydronium ion, and here we have a hydroxide ion. And it turns out, even in 100% pure water, a little bit of this happens. So if we have water out of lots and lots and lots of water molecules, every once in a while, two water molecules will combine, transfer a proton from one to the other, and produce hydronium ion and hydroxide ion. What we say is that water auto-ionizes just a little bit. It makes its own ions. It does this naturally. And it only does this, like once out of every, or about one out of every 10 million water molecules at 25 degrees Celsius do this. It's a very, very small amount, but it does it a little. And if we write H2O plus H2O as simply 2H2O, and the products of H3O plus and OH minus, and a double arrow indicating equilibrium, we have an equilibrium expression which should have an equilibrium constant. And it turns out that, of course, it does. Here's water auto-ionizing a little, written out explicitly. Here the double arrow is written kind of representing that there's not very many of the water molecules that dissociate, so small arrow going to the right. Most of the water molecules stay together, so that's a big arrow going to the left. And the K for this is H3O plus concentration times OH minus concentration. We call it a K sub W for water. So this is the auto-ionization or ion product constant for water. And it turns out that at 25 degrees Celsius, this product is 1.0 times 10 to the minus 14th. It's a different value at a different temperature, like with equilibrium constants in general. But this relationship, H3O plus times OH minus concentration equals this constant, that's true for all solutions, not just pure water, but it's true for acidic solutions and for basic solutions. And here's a little bit of a Lewis dot structure / molecular level representation. And here's some water molecules. And one of these water molecules, one of many, only one of very, very many water molecules, will transfer a proton to a different water molecule. And so we have an acid and a base. Water actually, this molecule acts as an acid because it donates a proton. This molecule acts as a base because it accepts a proton. We produce conjugate acid-base pairs. And substances like water that can do this, that can function as both an acid and a base, depending on the circumstances, or as an acid or a base, depending on the circumstances, are called amphiprotic. They're sometimes also called amphoteric. So these are substances that can function as either an acid or a base, depending on the circumstances. Okay, so back to pH and H3O plus, or H plus for short, concentration. Here's a pH scale once again, where we have the pH and its corresponding H plus concentration. And now we can bring in, after noting, here are some representative solutions and their pHs ranging from, in this case, 0.1 molar HCl through 1 molar HCl through 1 molar NaOH, and a bunch of common substances in between with their approximate pH values. But now we note that solutions, aqueous solutions, contain not just H plus, but also OH minus. And here is what we get. And a couple things to note: the H plus concentration times the OH minus concentration always ends up equaling 1 times 10 to the minus 14th. So 10 to the negative 2 times 10 to the negative 12th is 10 to the minus 14th. 10 to the minus 9th times 10 to the minus 5th is 10 to the minus 14th. pH is the negative log of the H plus concentration. So if the concentration is 10 to the minus 6 molar, pH is negative log of 10 to the minus 6, which is 6. And like with pH, we can also define something called pOH, which is the power of hydroxide, if you will, and that is the negative log of the hydroxide ion concentration. So if the hydroxide ion concentration is 10 to the minus 11th molar, the negative log of 10 to the minus 11th is positive 11, so the pOH is 11. And notice that just like H plus concentration times OH minus concentration always equals 10 to the minus 14th, pH plus pOH always adds up to 14. So here's a summary of the water ionization, auto-ionization, the ion product constant, K sub W, and the other mathematical relationships for aqueous solutions in general. So K sub W equals H3O plus concentration times OH minus concentration, and that equals numerically 1.0 times 10 to the minus 14th at 25 degrees Celsius. pH is negative log of H3O plus. pOH is negative log of OH minus. And pH plus pOH adds up to 14. So, armed with these relationships, we can now do a problem involving all of them. This question has a 0.025 molar HCl aqueous solution, and we are to determine the concentration of H3O plus, the concentration of OH minus, the pH, and the pOH for this solution. Well, first of all, note that HCl is a strong acid, and strong acids fully dissociate, so if it's 0.025 molar HCl, then it's 0.025 molar for its H3O plus concentration because of that full dissociation. And if we know the H3O plus concentration, Well, that was one of the things we wanted to find out. And if we know the H3O plus concentration, then we can find the pH, because pH is negative log of the H3O plus concentration. So this is negative log of 0.025 molar, and that works out to be 1.60. So now we've got the H3O plus concentration and the pH. Let's move on and find the OH minus as well as the pOH. And these can be done in a couple of different orders. In this case, I'm going to choose to use the ion product constant, or the auto-ionization constant for water. H3O plus times OH minus equals 1 times 10 to the minus 14th. We know H3O plus, so we should be able to solve for OH minus. And when we do, dividing both sides of this equation by H3O plus, we get OH minus equals 1.0 times 10 to the minus 14th divided by H3O plus concentration. The H3O plus concentration found previously is 0.025 molar. And again, we have to do concentrations in molarity. And when we divide this out, we get 4.0 times 10 to the minus 13th molar. And now the last thing is to find the pOH. And pOH is negative log of OH minus. Having just found OH minus concentration, we can take the negative log of that, and that gives us the pOH, and we get 12.40. And then, perhaps worth noting, previously we found the pH to be 1.60. We can confirm we did things right here, because the pH, 1.60, plus the pOH, 12.40, adds up to 14.00, which is what it should do. And that is it for an introduction to pH and pOH.